Deep inside the Khao Wang Kamen rainforest, thousands of interconnected species thrive in a delicate, ancient balance. Hidden within the limestone caves here rests the Kitti's hog-nosed bat. Weighing less than a penny, the world's smallest mammal relies entirely on the surrounding foliage to hunt and survive. This image shows a stark, dividing dirt path, separating dense tree plantations from terraced crop fields. Ecologists call this the edge effect, the abrupt, vulnerable boundary where pristine wilderness meets human expansion. During the dry season, farmers clear those adjacent fields. The resulting fires easily jump the dirt paths, tearing through the forest canopy and destroying the fragile hunting grounds inside. Securing the interior ecosystem requires locking down these specific geographic borders, but the sheer perimeter of Khao Wang Kamen is too vast to monitor effectively by foot alone. The physical shield for this boundary consists of local park rangers. They face brutal terrain. Thick vegetation limits visibility to a few feet, while unpredictable, razor-sharp limestone slopes make every step a calculated risk. A dozen rangers cannot effectively sweep tens of thousands of acres. Deploying them into the dense brush without a specific target drains their energy and risks their safety. To protect the forest effectively, they have to stop reacting to the terrain. They need a way to see the entire jungle before they even lace up their boots. Researchers from the Plant Genetic Conservation Project are achieving that top-down vision by accessing data from Sentinel-2 satellites. These satellites capture infrared light bouncing off the Earth. By measuring that light, researchers calculate an index called NDVI, which reads the health and density of the leaves below. This map displays NDVI data over Khao Wang Kamen. Deep green areas highlight thick canopy corridors where bats feed and fires find fuel. Knowing these locations tells rangers what to protect, but offers no safe way to walk there. To solve the navigation problem, the team pulls a second layer of data, radar-generated topography. This measures the exact steepness of the mountains to pinpoint deadly drops and impassable cliffs. Layering the health of the trees over the steepness of the rock turns the physical jungle into a mathematical landscape. Every acre becomes a calculated mix of conservation targets and physical hazards. The AI algorithm digests these layers to create a friction map. It assigns a difficulty score to every single square meter of the forest. This simulation shows the AI's logic. Red zones indicate steep, dangerous slopes to avoid. Green zones identify high biodiversity areas requiring urgent patrolling. The algorithm tests millions of variations, seeking a route maximizing time in green zones while bypassing red ones. This satellite imagery reveals the final calculation. A bright pink optimal patrol route snaps perfectly into place, threading the needle between impassable mountains while hitting the critical canopy targets. That route represents a calculated tactical compromise. It keeps human patrols out of harm's way while deploying them exactly where the ecosystem is most vulnerable. Mathematical models only work if they hold up in the mud. The final step is ground truthing. Rangers follow the AI's coordinates using handheld GPS units, stopping along the predicted route to capture street-level photographs of the forest edge. They are physically verifying the buffer screen. They check if the density of the trees on the ground matches the satellite data, confirming the foliage is actually thick enough to block agricultural winds and stop fire embers. This data serves as a precision navigator, allowing the team to bypass empty stretches of forest and focus their strength on the exact coordinates where human activity threatens a habitat. When the rangers finally enter the dense jungle canopy, they step forward into the unknown with absolute, unwavering tactical certainty. This integration of space-based data and ground-level action is a direct continuation of Princess Maha Chakri Surindorn's Plant Genetic Conservation Project. The initiative operates on a core ethos: to love our resources is to love our nation. Technology simply provides a modern, precise tool to execute that duty. Protecting these ancient landscapes depends on a precise alliance between human field experience and artificial intelligence.